I'm going to look at a couple more counting examples for this section. Here we have a problem near and dear to my heart, ice cream. And we have 4 different toppings available. We're looking at the number of ways we can create a dish of ice cream, and we're assuming the order of toppings does not matter. Whatever you believe, in this problem, order does not matter. It does not matter if the chocolate goes before the butterscotch or the butterscotch goes before the chocolate. Doesn't matter. So we have to run through our different options here. It is possible, even though I consider this sacrilege, no toppings is a choice. You can have a plain old boring, uninspiring, bland dish of vanilla ice cream and nothing else. That is possible. There's one way to do that. Put some vanilla ice cream in a bowl, start eating. One way to do that. We could choose one topping. And we have 4 choices, 4 ways to choose one topping. 2 toppings. Again, order does not matter. So chocolate and butterscotch would be the same as butterscotch and chocolate. Caramel and sprinkles would be the same as sprinkles and caramel. So we have to eliminate all the repeats. This is an NCR situation. 4 toppings, choose 2. C2 ends up being 6. And by the way, we had that in our first 2 parts here. Here, we really have 4C0. And here's 4C1. 4C2. So we start to see a pattern here. The number of ways is going to end up being 4C0, 4C1, 4C2, 4C3, and 4C4. This is 1, 4, 6, 4C2 is 6, 4C3 is 4 again, and then this is 1. So if we add all these up, there are 16 ways that we can create a bowl of vanilla ice cream, choosing among 4 toppings. Choosing no toppings, 1, 2, 3, or 4. One thing I want you to notice in this problem is 4C1 and 4C3. They're the same value. And that's going to show up in other areas as well. For instance, let me just make one up. 7C3 will equal 7C4. 8C, say 5 will equal 8C3, and so on. Reason for that is in the formula for NCR. Remember that NCR is n factorial, r factorial, and minus r factorial. So let me use 7C3, 7C4 as an example. 7C3, using the formula. 7 factorial, r is 3, n minus r gives me this. 7 factorial, 3 factorial, 4 factorial. And if I use 7C4 using that formula, I end up with this. 7 factorial, 4 factorial, 7 minus 4 factorial. And notice these are the same. The only difference is the numbers in the denominator, the factorials in the denominator are reversed, which, because we're multiplying, doesn't change the answer. Simply flipping the factorials around will give us the same answer. That is true of any two NCR pairs whenever the r's add up to be n. Here we have r is 3, r is 4. They add up to be 7. 5 and 3 add up to be 8, which is also n. And we get the same thing here. This is 5 factorial times 8 minus 5 factorial. 3 factorial times 8 minus 3 factorial. So on the left, we would get in the denominator 5 factorial, 3 factorial. In this denominator, we would get 3 factorial, 5 factorial. The same thing. Same thing going on in here. 4C1, 4C3. This r plus this r adds up to be the value of n. So that is something to look for in a problem like this. Whenever you have r's, pairs of r's that will add up to equal n, we know that those spots will be the same value. One more problem to take a look at to wrap up this section. And let's deal with just this part first. We have a license plate, any combination of letters and digits. I should add to that 6 letters and digits. Clarify that. How many plates have at least 1 digit? Now there's a couple ways to do this. One method, which I call the we don't want to do this method, is to figure out how many have 1 digit, how many have 2 digits, how many have 3 digits, 4, 5, and so on. Every single possibility. And oh, by the way, when we do the 2-digit one, the 2 digits could be here, or they could be these 2 spots, or they could be these 2 spots, they could be these 2 spots, they could be these 2 spots. Doesn't this look fun? Those are just all the 2-digit locations. Then we get to 3 digits. So maybe these are the 3 digits. Or maybe the 3 digits are here, here, and here. Or maybe they're here, here, and here. Or maybe they're here, here, here. Again, we have to do each one of those individually. Not fun. Method 2 is there's a shorter one. And it revolves around this phrase. At least 1 digit. So, we're going to look at it from this perspective. What we don't want. What we don't want is all letters. In other words, we don't want a situation with no digits. We want this license plate to have at least 1 digit, which means it does not have 0. digits. It's all letters. That's what we don't want. So let's look at the total number of plates, no restrictions whatsoever, minus all letters, or we can even say minus no digits, and that's going to equal all the plates with at least one digit. That's going to be our strategy. Calculate the total number that exists, subtract the ones we don't want, and we're left with the ones we do want. Sometimes it's easier to calculate this way than it is to try to calculate every single other possibility. Because there are so many situations of what we want, it's easier to calculate what we don't want and eliminate it. So that will look like this. Here's the total. So we have letters and digits. We have 26 letters, 10 digits. That's 36 possible characters that can go into each spot. So 36, 36, 36, 36, 36, 36. That's 36 6 times. 36 to the 6th power. Minus all the license plates that have no digits. In other words, they're all letters. So if I only use letters, I have 26 letters, 26 letters, 26 letters, and so on. 26 letters 6 times. If I do this calculation, I will have all the license plates that have 1 digit or 2 digits or 3 digits and so on, simply by eliminating the ones we don't want. It turns out this is going to be a pretty big number. Let's see. There, we got there, we got there. That's 1,867,866,560 license plates. That's a lot. That's plenty. For the state of Wisconsin, that's definitely plenty. Again, here was our strategy. Calculate the total number of license plates that can be made from this criteria. 36 possibilities for each position. Subtract the ones that we do not want. Subtract the ones we do not want. And then what we're left with is this. Second problem is very similar. Let me slide this down a little bit here if I can. Give us a little more room. There we go. Second one is a little different, but it's pretty similar. How many plates have at least 2 digits? So we'll do a similar approach here. We'll take total minus no digits minus 1 digit, because we don't want that one either now. And that will equal at least 2 digits. By eliminating this group, which we already did, and eliminating this group, we'll be left with this criteria. So I'll take a similar approach. I know this is 36 to the 6th. No digits is 26 to the 6th. Now I have to calculate one digit. The number of license plates that have one digit. So let me take a look here. Here's my license plate, and this could be number, letter, 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 or this could be letter, number, letter, 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 and so on. There are 6 different places this digit could be. So once I get my first set here, I have to multiply it by 6 to account for all the possibilities where that number could be. I have 10 letters to choose from. I have 26 letters to choose from, and I will do that 5 times. And now I have to move that digit around, because if I just do this, I'm saying that's in the first spot. Well, now maybe it's in the second spot. Maybe it's in the third spot. Maybe it's only in the fourth spot, and so on. I have 6 positions to choose from. I want one letter. I'm sorry, one number. I want one of those positions to be a digit. 6 spots the digit could be, I want it in one of them. So this accounts for all the possibilities. So now we'll do a similar calculation. We already know what 36 to the 6th minus 26 to the 6th is. From that answer, we're going to subtract 10 times 26 to the 5th times 6. We're still going to get a pretty large number. So we've gone from 1.8 billion down to about 1.1 billion by removing all the one digits. And again, the other way to do this, if you don't want to do it this way, you have to calculate all the 2-digit possibilities, all the 3-digit possibilities, all the 4-digit possibilities, and so on. And that's a lot of things to add up. By subtracting what we don't want, we get there much more efficiently, a lot more quickly.